Yes, so my talk is called How to Implement Words Efficiently. And we all know how to implement words efficiently, don't we? Well, actually, what happened is, and what inspired me for this research, is that in the course of another paper that I'll be presenting tomorrow, I think, I found I had these measurement results. And especially there were some funny results for EuroForth, especially for the CD16 sim application benchmark. And yeah, at some point I contacted Leon with it and showed him, yeah, there's some iCache misses and dcache misses, and this looks like there's some code close to data. But we didn't know what the problem was, and we looked a little bit into it, but we didn't find it. And then about 2 months later, so I was wondering, so why is VFX so much faster than GeForth on CD16 sim? And then I found that CD16 sim is doing lots of create DAS defined words. And basically 2/3 of the execution is just with one DAS definition, in GeForth at least. And VFX inlines that, and that's why it's fast, and GeForth doesn't, and that's why we have this big difference. And then I thought maybe this has to do with the reason for why EuroForth is so slow, and I looked at the code that EuroForth generates, and then I found the problem. And just so you can interpret this, so the one is the GeForth with from 2024 with the optimization that I will be talking about tomorrow enabled. And basically, the dark green one is without this new optimization, and the light green one is basically threaded code. So light green one is like threaded code, yeah. So basically we'll find that call pull is the problem, and where does this come from? So all the red stuff I'll be presenting here is always native code. So the black stuff can be something else, typically data. And yeah, in the good old days of indirect threaded code, when we had a definition like this, so we had something that worked somewhat like a constant, but we can actually modify it, so we can't inline the number. And we define such a constant. This would look like this. So we have here myconst with its header, and it has a code field address that contains docall, and then we have the threaded code for create, comma, and parendas. And after that, we have some native code, and I'll come into that yet. And then we have the threaded code for fetch and the exit after all, so behind, coming from the semicolon here. And for this myconst 5, for this word 5, we have here the header 5. Then, and that's the interesting thing, this code address in the code field address points to this native code inside the definition of myconst. And then we have the data 5. And the reason why this is we have one indirection, but we need to find the body address, and we have the body address because this is our where our threaded code points to at some point, or the execution token on the stack for execute. We need the body address to access this 5. we need the DAS code address, and we need, so the DAS code address is the address of this piece of code. And we need a code address for actually performing the thing. And so we also need this piece of code. And how to do it? Well, this is a technique invented apparently by Don Colburn. No. Sanderson. Dean Sanderson, yes, sorry. By Dean Sanderson. And so you all have your history.
It's actually Dean Sanderson and Mike LaManna.
Okay.
Mike LaManna had a chart on the wall, and it said all the little does and what they do.
Great. I'll contact you about the exact name because I want to update this in my paper. Sure. All right. Yeah, so this basically it points to here. Then the call goes to the do-does, which is here. And how does it get this address? Where does it get this address from? It pulls it from the CPU stack, and that's why we have here a call and not a jump. So the call pushes the address that points here on the CPU stack, and here we pull it, and we put it in the instruction pointer of the threaded code, and which means that when we do the next, the execution will continue at the fetch. Right. So then this must have been in the late 70s when this technique was.
When you say data and return and CPU stack, what is the CPU stack?
The CPU stack is the stack on which call pushes its return address. So it's for native code return address. Yeah, so when people switched to native code systems in the 1990s, they will use this technique for good reasons. So basically, what I present here is rather simplistic. You can do various optimizations, but I mean, this is just a sketch. So the problem is that typically in subroutine threaded code and naive native code, when you have 5 somewhere along the code, so this 5, you will have a call to this piece of code, and this call will actually. Where should it call? We still need this body address, and we need this code address. So we use this call pull technique again. We call here, and this call calls this piece of do myconst, which I abbreviate with do MC here, and to get the body, we pull it back from the CPU stack. And yeah, then we do the rest. So here is the fetch, and the push toss to data stack is also part of the fetch, and the return is this here. Right, and the reason why we do it here, in spite of not having any threaded code to deal with, is that we don't have the code field address in the W register. Like classically, threaded code put the code field address in the W register, and with normal doers, we could get the body address from the W register, and with the do does we needed the extra thing. And with native code, we don't have the code field address in a W register, so we also need it with only having one code and one data. So yeah, the solution, the possible solution, and the actual used solution in some cases is to use this call pull technique, and it's also used without does, as we will see in some cases. So what is the problem? There are performance pitfalls. One is called false sharing. So basically, when we have modern CPUs since the 1990s have caches, and these caches are organized in cache lines with a granularity of 64 bytes typically. I mean, there are variations, but 64 bytes is a typical size. When you have the same data, you can have the same data in two different caches. And for example, you can have it in the D cache and in the I cache at the same time, but only if it's only read or executed. As soon as one of the caches is written, so you can actually only write to the D cache, the data cache, the other is invalidated. And this false sharing is a problem normally with multi-threaded code that runs on different cores. When they put two pieces of data side by side in the same cache line, you get false sharing and slow code. And in our case, with the call pull technique, we get it between the instruction cache and the data cache on architectures where the instruction cache is cache coherent with the data cache. And this is Intel and AMD CPUs and the IBM mainframes, actually. So on ARM and so on, you don't have this problem. But on ARM, when you change code, you have to do some extra software work. But that's something different. Anyway, so here in our example, we have from our last thing here, this piece that's called doMC and the 5 in the same cache line. And it's both in the data cache and in the instruction cache. And we see from the tag here that this is the same cache line. It's the same, it has the same tag. And they have some common memory subsystem below the separate caches. And so when this is invalidated, it later, and the written, and then it tries to execute it again, it asks this cache and it gets a broadcast out, and this cache will then say, oh, I have this. And through a lot of work, the iCache will get the code again. And this takes around 400 cycles on, well, the whole thing with writes and invalidate and then loading it again. So on Intel P processors, I've measured about 400 cycles and sometimes only 200. I don't quite understand when it's 200 and when it's 400. And on the Ryzen 5800X, it's about 100 cycles. So should we get all Ryzen processors? Actually, we should avoid this. Even 100 is very expensive. And so this is called false sharing because it's these are actually it's just because the data and code is adjacent. So it's actually, you're not modifying the code or anything. You're just modifying data that's close to the code. So that's false sharing. True sharing would be when you modify the code. Yeah, and that's also expensive. And then you have to do the expensive thing on ARM and so on too. So the other cost of the call pull is that it gives you a return misprediction. So when you do a call 5, it pushes, so on say AMD64, it pushes the return address R on the CPU stack, the one that's pushed by call. And there's also in the hardware, there's an additional structure which is called the return address stack, which is used for branch prediction. So as long as they are in lockstep, it's okay. I mean, you can do, on the CPU stack, you can push additional things, but when you then do a return, it should be at this point again. So when you return to I, it should be, the CPU stack should be using this return address. The next thing is to call doMC, and which means, yeah, we now have R and the body of 5 on the CPU stack and on the return address stack. And the next thing is that we pull the body of 5 from the return stack, from the CPU stack. And now these two stacks are no longer in lockstep. And when we finally get to the return, it tries to return to the body of 5, which is wrong. And then it takes 20 to 30 cycles to actually recover from this branch misprediction. So, the first case is the one from, so this, we have a number of Microbenchmarks. The first one is inspired by the case in CD16 sim. So we have some created word that has an empty does thing, which is actually, interestingly, what happens in CD16 sim. And I asked Brad Eckert why he did that, and he doesn't remember it, unfortunately. But I mean, such things happen, so we have to be prepared for it. And here we have a microbenchmark that makes a number of iterations, and in each iteration it increments the value in this created word. Yeah, we see here the performance. Yeah, so what I forgot to tell earlier is, yeah, after the second thing, when I found out that why EuroForth is slow, I told Leon, and he swiftly produced a version that didn't have this particular problem. Okay, wow. All right, but it still was swiftly. For me, it was swiftly.
Excuse me. The comments are too quiet. Speak up.
Yeah, no one needs to hear that.
Okay.
Just really quickly, the capture froze. Do we want to try to fix it, or are we happy with just filming like that?
Yeah, up to you.
Okay. Can I try to fix it?
You can try, but let's continue.
All right. So, yeah, we see here that EuroForth in RC87, which was before the fix, takes 434 cycles for each iteration of this microbenchmark. And this despite only taking 15 instructions. And what we also see is that there are some I-cache misses, some D-cache misses, and some branch mispredictions. Okay.
No,
that's...
go on. You'll be there in a second. That's why I asked.
All right.
I wasn't aware it was going to break. Well,
okay.
It should be back.
Yeah.
Oh, sorry, I think you have to redo your
No,
thing. No, it's back, it's back. Okay.
So, yeah, and all the other systems somehow managed to get this, to actually run this quickly. But this is not always the case. So here we have a case. So after I started with this, I thought, well, what else could be going wrong? And did a number of micro benchmarks that tested various variations and other things where I thought that such things could be involved. And here's one that was pretty hard on several systems. So basically, yeah, this is more or less similar, except that here we have some floating point on the some floating point stuff in the DAS, which is not inlined by VFX, and so even when it's compiled, it has this penalty. But here we also have a case where we actually do not compile it, but execute it, and these cold pull things come out usually when stuff is executed.
I think that's the run of time for defer that is actually causing it.
There is no defer here.
Sorry?
There is no defer here.
No, but there's an indirection that's...
Yeah. So yeah, so this is actually execute, but actually for VFX you also get a slowdown when you write here Z2, and yeah, and so when it's actually compiled. Yeah, and you see typical. Also, we have these large numbers of cycles for various systems, and also large number of cache misses. And here we, see one cache miss. And one thing is interesting: EuroForth doesn't one return misprediction, and EuroForth doesn't mispredict returns because it doesn't use a return instruction for doing further returns. So it uses call pull, but it doesn't use return for doing fourth returns. It doesn't use the ret instruction. Anything else? Yeah, that's it. So do such problems only occur with DAS? No, here we have a create X without DAS. And we see when we so here we tick the X, and here we execute it, and here we see, we see some slowdown in EuroForth and VFX. And here this affects both RC87 and 89, so I just write SF. Yeah, that's because the created word is implemented with call pull. At least when it's executed. So lots of these things come out with execute, as I mentioned. So what about different is? Here we have this Microbenchmark is somewhat involved. So what it does do is we have this deferred word W, and it's in every iteration we change what it does. In one iteration it does -0, and in the next iteration it does drop, and then again -0, and in the next iteration drop. And here we see, again some slowdown in EuroForth and VFX because I think of call pull. And here we also see a slowdown in LXF, which is a system by Peter Feld, and because he implements deferred words with jump patching, which is true sharing and gives you the same slowdowns on these kinds of machines. And he actually has reacted in the meantime, and he said, he is actually working on a new version that that doesn't use this technique, and he used in this older version he used it intentionally because he thinks that it doesn't happen so often. So the next thing is what do we see when we do defer without is. And this is what we have here. We just call W, which is -0, which is a constant containing 0, and drop this 0. And here we see that EuroForth and VFX. So we don't have I or D cache misses because we don't have any writes. So the fault sharing is not a problem here, but we still get the branch misprediction from the call pull. We see that, I mean, it's not these hundreds of cycles, but it's still quite a bit slower than some of the other systems. So call pull is really not a good idea, even when there's no write involved. So these were microbenchmarks. What about applications? So the question is, how do you know that an application is affected? You only know it because you know that it should perform better. But how do you know this? I mean, I didn't know this until I actually compared the result of SwiftForth with the result of other Forth systems. So yeah, and one way you would also do this is you compare the iCache misses with other Forth systems. So you get an indication of fault sharing from the iCache misses. You get an indication of the return mispredictions from the branch mispredictions, but there are also natural causes of iCache misses and branch mispredictions. So in order to be sure, you have to compare with a different Forth system. And the only way to be sure that it's not this problem is to implement the words using techniques without these performance pitfalls and finding out that there's no speed up. So, and yeah, basically in SwiftForth this was implemented with an all-nighter by Leon using became available with RC89. And we see that, yeah, CD16 sim became faster by almost a factor of 5. But it also helped other applications like LexX and the other application benchmarks not so much. And interestingly, I mean, these first 5, they are application benchmarks. So they benefit. And these are, the other ones are small benchmarks, or not, some like Pentomino and SHA 512 is not small, but they are not idiomatic Forth code, I would say. So it's like sometimes these small benchmarks can be quite misleading. So you would think there's no problem when you look at the small benchmarks. But when you look at the application benchmarks, you see there's a problem. So, oh yeah, I did. Somebody started me late.
I giving you extra time for that.
Okay, so yeah, how to avoid call pull? One option is trampolines. So, which is basically for each word, like 5 in this example that we have seen, we create a small piece of native code that does basically what this assignment to the W register does. It just here, instead of the W register, we use a register called body, and we assign the constant 5 body to it, which points to the body of 5, and we jump to do myconst, and do myconst then does this fetch CMIS. Yeah, and this keeps code separate from the data, so you don't get fault sharing, and you get the body address without pulling from the pulling a called value. The return address of a call, so you don't get the branch misprediction. And that's what LXF does, and that's why LXF usually gets good performance on these micro benchmarks, except for the ones where different is involved. So another way is to use an intelligent compile comma, and basically you all have been using this, but intelligent compile comma means depending on the word type and word characteristics, you do some special compile comma action and not just compile a call to the word. And yeah, and basically that's what gave, for the original example, gives the good speed for VFX. And in our example, so here we compile 5 inside another word called my5. I mean, it's quite simple, a very simple-minded example. And what we see, what the special compiler comma implementation does is it assigns the address of this body to a register called body, and then performs a call to the doer, which is do does. And in this case, the call is a tail call and is optimized. So that's why we have a jump here. And when we actually look at it, it's the same piece of code that we have for the trampoline over here, except that this is associated with this word. So actually, for generating the trampoline, we can actually use this intelligent compile comma. Yeah, it keeps the code separate from the data. It gets the body address without pulling a called return address, the return address of a caller. And yeah, it can be used to generate the trampoline. And it does not help for execute or defer because we don't use compile comma for execute or defer. So another way is to use a code field in the classical indirect. So like an indirect threaded code does it. So where the code field contains a data, piece of data, which is the address of a code, of a piece of native code. And we use, I mean, you don't want to do this for every call in your compiled code, because then you would have to, before every call, set up W or something to point to this address. But you can do it for stuff like execute and defer, do defer. And yeah, here we see how execute looks like. So we say, so execute gets its address from the data stack. So we pull it from the data stack and put it into the register W, and then we get the code address from W and do the jump to it. So we get the code address from here and jump to it, or the code address from here and jump to it. Yeah, so this works fine for execute and deferred word, and it's for naively compiled code. It's not particularly efficient, but if you use an intelligent compile comma anyway, you can use this kind of thing for executed and deferred words. So how to implement deferred words? Well, that's just, I mean, most of you do it right anyway, and Peter Feld has said he's going to do it right too. So just use a data field and an indirect jump, and so don't patch native code jumps. So in conclusion, we see slowdowns from call pull because of false sharing and because of return mispredictions. We see big slowdowns in microbenchmarks, varying. So basically most systems are actually affected in one way or another in these microbenchmarks. So how much slowdown do we see in applications? We know it when we fix it. Before that, it's really hard to know. It's possible to avoid call pull using either trampolines or, no, it's not either or, you can use trampolines all the way. you can also use the intelligent compile comma, and as an alternative to trampolines, you can also use the code field, which works best if you combine it with the intelligent compile comma. And you use the data field for deferred words. And you can find the microbenchmarks at this address. Thank you.
Thank you.
Thank you.
How do you measure those branch mispredictions?
I use perfstat from under Linux. So perfstat minus e branch misses. Yeah.
Okay. Anyone else? Going once?
Can you tell us maybe how big is really the difference between the patching a native jump and having the what you said, just using an indirect jump? How big is the difference there, ignoring all else?
I'm not sure what you mean. I mean, do you mean this one? I mean, here LXF patches and takes 400 cycles because of true sharing.
Right. Okay.
And with an indirect jump, I mean, it's like what EuroForth or GeForth does.
And what would a correct direct jump be on that scale? Would it be a lot faster than the indirect one? That's what I meant.
You mean if you don't have this true sharing problem,
Yeah.
because you actually don't do is it faster? I mean, it's like, yeah, you see here, LXF takes 6 cycles per iteration for this benchmark,
Okay.
and GeForth takes 8.4, which is, but GeForth uses 35 instructions for it. If it only used 12 instructions, I think the difference would be 0.